This data visualization tracks the survival rate of small and medium businesses following a cyber attack. 57% of these organizations cease commercial operations entirely after a breach occurs. That closure rate is driven by cascading damage. The attack forces the business to halt operations for days, while regulatory bodies levy massive fines for non-compliance with frameworks like GDPR. Ultimately, client trust is often irreversibly lost. This high failure rate reflects a total structural collapse of the targeted architecture supporting the network. Cybersecurity engineering is guided by a foundational axiom called the CIA Triad. This framework consists of 3 supporting pillars: confidentiality, integrity, and availability. In order to fully understand the load-bearing capacity of these 3 pillars, we must subject them to a specific stress test: ransomware. By reverse engineering a ransomware attack, we can see exactly how it dismantles the CIA Triad. From there, we'll apply the mathematical principles of cryptography and subnetting to architect a resilient defense. Take a private medical clinic storing sensitive patient records. In a vulnerable setup, this clinic operates on a single, unsegmented flat network. In this context, confidentiality requires that patient records are strictly inaccessible to anyone but authorized doctors and staff. Integrity provides a mathematical guarantee that data remains perfectly unaltered. A digital prescription, for example, must remain exactly as written during transit and storage. Availability ensures that the systems and data remain accessible the moment the organization demands them. A ransomware payload enters the clinic's core database. Once the malicious code executes, it begins corrupting the central digital node and spreading through the system. Look at the node map. The availability pillar fails, cutting off operational access. Next, integrity collapses as encryption scrambles records into unreadable blocks. Finally, the attacker exfiltrates the data externally, destroying confidentiality and triggering compliance implications. Ransomware causes a simultaneous multi-axis failure of the entire triad. Defending against this requires layering different architectural protections. To build a defense, we start at the beginning of the attack timeline, the unauthorized perimeter login. Relying on a password alone is structurally insufficient to protect confidentiality. Once a single string of characters is compromised, the attacker has full access. Multi-factor authentication, or MFA, creates a mandatory requirement for layered identity proofing. This requires at least 2 of 3 distinct categories: knowledge, like a password; possession, like an app or hardware token; and inherence, which refers to biometric data like fingerprints. If the perimeter is breached, the payload, the data itself, must have inherent defenses. This is where cryptography is required. This split screen shows encryption defending confidentiality. A key transforms plain text into unreadable ciphertext. Symmetric encryption uses a shared key. Asymmetric uses a public-private pair. On the right, hashing protects integrity. A dataset passes through a mathematical function, generating a unique alphanumeric hash string. These hash digests are highly sensitive. Altering even a single bit of the data radically changes the resulting hash, which instantly exposes malicious tampering. MFA protects the entry points, and cryptography protects the files. However, a successful infection can still spread laterally across a flat network. In a flat network, every device shares a single broadcast domain. This lack of segmentation allows malware to move between devices without resistance. A compromised host in a standard /24 network can spread ransomware to up to 253 other machines. We solve this by implementing subnetting, an architectural solution designed to minimize the attack's blast radius. This IP calculator shows a 32-bit binary address, separating network bits from host bits. By reallocating a host bit to the network, we shift the boundary, updating the subnet mask from /24 to /25. This logically divides the 254 host pool into 2 isolated subnetworks. In a clinical environment, we can isolate medical records on subnet A and move high-risk traffic, like guest Wi-Fi, to subnet B. Network firewalls positioned at these newly created boundaries enforce strict access controls between the subnets. This topological isolation ensures that the physical architecture arrests the lateral movement of malware, preventing a localized breach from collapsing the core business. Viewing the complete network model, we see how these isolated subnets integrate into a secured system. On this macro-level map, All defensive layers operate in unison. MFA secures the endpoints, cryptography locks the data structures, and subnets isolate the departments. The CIA Triad is now structurally solid. Cybersecurity is a product of rigorous architectural discipline and engineered resilience that exceeds the capabilities of any single software solution. This multi-layered approach ensures that the failure of a single endpoint or system does not trigger a total organizational collapse. By architecting systems strictly around the principles of confidentiality, integrity, and availability, we build digital infrastructures capable of surviving the modern threat landscape.